Welcome to another exciting episode of AP Chemistry here at Spain Park High School. Today is Monday, February the 7th, 2022. That just sounds like in the futuristic time. If you're enjoying these videos, please feel free to subscribe to my channel.
Leave a like button.
Comment.
Oh, well, we don't want to show everybody's grades. Okay, or on my emails. All right, so 2005, Form A. Whoop. We must have had a power outage. Here.
They used to do like the commentary and the sitcoms, like,
Yeah. Okay, so here we go. So here's 2005, and we're given this information. So go ahead right now. I think we touched on this one. Did we already do this on one?
Yeah.
We did A.
We did that.
Oh, no, we did
part
all
A,
that.
did we
Never
do part B?
We did B too.
We did this part down here,
Yeah.
okay? We didn't do this part. Okay, this is the part I want us to focus on. Because notice now that we have concentration versus time. What does that trigger in us that we need to do? Rate law, but which rate law? You have the differential rate law and you have the integrated rate law. Because it's time, we want to use the integrated rate law. Okay? Now, we may or may not have to do this, but it tells us the catalyzed decomposition of hydrogen peroxide is represented by the following. The kinetics were studied and the analysis of the results shown it is a first order reaction. So underline that. It's a first order reaction. So they tell you that. So we know which equation we need to use now. Correct?
Right.
And what equation are we going to use? We're going to use what?
Rate.
It's the natural log one. Okay? The natural log of concentration at any time t is going to equal negative kT plus the natural log of the concentration initial. So, when you turn it over, you go to this next page, what needs to be on the y-axis then? For it to be linear. Okay, make sure it's on the screen. What goes on the y-axis when it's a straight line on a first order? No. ln, not of x, ln of, what's the reactant? Hydrogen peroxide. So it's the ln of the concentration of your hydrogen peroxide. Because y equals mx plus b, in a first order reaction, that's what's going to be on the y-axis. In a second order, if it was second order, what would go on that y-axis?
1 over.
1 over the concentration of H2O2. Okay, so don't just go generic on the x. You use the reactants that are given in the data. So, what are the units for the rate constant, K? So if it's first order, what are the units for rate law constant? And you can even use, again, when you're trying to figure out, oh shoot, I can't remember. We'll go back to the differential rate law, because the math's easier. Rate is equal to K times H2O2 to the first. Well, rate is always measured in, well, if you go back to the first page, is it molarity per, what's the time measured in?
Minutes.
Minutes? Okay, so that's the only thing you gotta double check is molarity per minutes. So it's molarity per minute is equal to K times molarity. So what are the units on K gonna be? Just 1 over minutes. Now, it doesn't say justify your answer, it doesn't say explain, you just write it. It's a 1 point for forget it. So if it doesn't say justify or explain, you just put your answer. Does everybody understand the math? The rate is always molarity per time. So make sure the rate is the change in molarity over how long it took to do that change in time. So we always measure rate. Take K, and brackets are always molarity.
If it was to the second order, would it equal K times M squared?
Yes. So then one of the m's are gonna cancel out, so then it would be 1 over minutes times molarity. If it was second order,
So for this one, K equals 1 over minutes.
1 over minutes.
The vertical axis, you said it was ln of T or
H2O2.
H2.
It's gonna be the ln of what, oh, it's actually a little l, isn't it? Ln of H2O2. Again, if it was second order, it'd be 1 over H2O2. If it's 0 order, it's just gonna be concentration of H2O2. Now, on the graph, draw the line that represents the plot of the uncatalyzed. This is the catalyzed. What would the uncatalyzed look like? Just on, go ahead and take 30 seconds. See what you think it would look like. Make yourself make a decision on what it would look like. Okay, so what do we think? Where's it gonna start? Same place. So our starting point is gonna be here. So the whole key is I'm gonna have a steeper or less steep slope. It's gonna uncatalyze, means it's gonna go slower, so it's gonna take more time for the concentration to decrease, but it's still gonna be a straight line. And all you had to do is anywhere above the line, a straight line anywhere above the line.
Because catalyzed is faster.
Catalyze it, because when the catalyst always speeds up a chemical reaction. So uncatalyzed means it's gonna be slower, so the concentration will decrease at a slower rate, take more time for it to go down the same amount. Okay? Now, I'm gonna add in a 4. Well, let's just do it like that.
The fourth.
Okay?
It's the fourth eye. You know how there's a third eye?
What would be the concentration after 15 minutes? Okay, now, we went through and got the units, we're here, close enough. We got the units for K, but how can I calculate the actual value of K?
Use the values in the chart.
Use the values of the chart, right? Because I know the natural log of H2O2 at any time t is going to equal negative KT plus the natural log of H2O2 initial. Now again, that equation is given to you. That is my integrated rate law for a first order reaction. So, everybody has this all copied down. We want 15 minutes. So we're gonna come back and use everything here. So, the first thing I have to do is I have to find K. So how do I find K?
Plug in values.
Plug in values. And I would not use times 0,
That's the initial.
because that's gonna cancel this term out right there, okay? So we can just use 5, okay, 5 minutes. So the natural log of H2O2, so we're gonna take the log of the concentration, 0.78. That's at time 10, pardon me, at time 5, is equal to negative K times 5 plus the natural log of the concentration at time 0, initial. We could have used 10 minutes, used any one of them other than the initial. So make sure that you know how to do your logs on your calculator.
Switching them. There.
That's my algebra says I do it that way.
I think that's right.
Is there something for them?
Shouldn't it be negative K?
I put the negative in. It's probably gonna be a negative on the top divided by a negative 5.
Yeah. 0.04969.
0.00,
No, just 0.04969
one more digit,
versus
7.
7.
Okay? And we determined that the units on this was just per minute. Okay? So in order to be able to use the rate law, I have to know what K is. So now I know the actual numerical value of K. So now how can I find the time at 15 minutes? I mean the concentration at 15 minutes.
Plug in K and then you find it.
So I know this, so now I can just say, well, the natural log of concentration H2O2 at 15 minutes is going to equal negative K 0.0497 times 15 minutes plus the natural log of 1. That's the initial concentration. So, somebody get me an answer to what the whole right side of the
It's
Negative
0.7455 is equal to the natural log of H2O2, right? So well, how do I solve for H2O2 then? E to this power, right? Okay? So H2O2 turns out to equal, oh wow. Oh, that must be our girl spirit pack. Woohoo! Right there, on top of it, you can put it right on top of all these.
Yay! We're all stopping for the camera?
Wow, thank God. I'm here.
So you know how you do
said to solve.
You just go,
Does this change anything?
okay, so have you already done this one or?
No, I don't. Yeah, it does.
Okay. So what you want to do is you're just gonna go natural log, let's do the natural log button. No, natural log. Okay, and then put in 0.78. Okay, and then close the parenthesis. Okay, minus natural log, 1, close the parenthesis. I'd say equals, and then take that divided by, just hit divided by,
I like calculating.
negative 5. Point 0.497. 4969 rounds to
I used,
496.
I found my calculator.
It was the first thing in your text.
I found it in my car.
Okay,
Oh,
so,
that junk?
part 5. Part 5.
I have no.
Oh, fine.
Part 5. Okay, did everybody figure out how to do the logs, natural logs? Okay, so your calculator does the work for you, you just gotta know which buttons to push.
Thank you, Ryan.
Ryan.
That's why you learn math, so you can apply it to a real subject. Okay? So,
Oh, real stuff.
yeah. The next question is, what is the half-life then of this reaction? What is the half-life? What is by definition the half-life?
How long it takes for one molecule to decompose?
No.
For half of the,
Okay, so if I start at 1 molar, how much is left after 1 half-life? 0.5. How much will be left after 2 half-lives? 0.25. Okay? So, we can figure out the half-life,
14 minutes.
okay? But looking for time here. So, this is part 5. Okay? So I can then say, well, the natural, I need a marker.
Oh.
That was really weak.
Rimmed out.
Really weak. That was almost an airball.
That's okay.
The natural log of 0.5 molar is at T1 half is equal to negative the same K, 0.0497 per minutes, times T1 half, okay, that's what we're looking for, plus the natural log of 1. Okay? Now, when you subtract, that's kind of the same as dividing, right? That's the same, isn't this the same as natural log of 0.78 over the natural log of 1?
Yep. No, it's 0.78 over 1. That's what we did.
Yeah, 0.78 over 1, okay, is the natural log is the same thing as that, right? So what's this going, if we're doing on half-life, and we've got 0.5 over 1, obviously that's gonna come out to, actually, is it, do I have it backwards?
It's one.
Okay, that's right, so what's 0.5 over 1 gonna be?
It's 2. Wait, no.
1/2.
1/2, right? 0.5. What's the natural log of 0.5?
it is,
Negative. Oh, no.
I don't know off the top of my head, but.
What-
It's negative 0.69.
0.693, okay?
Oh, that's fine.
So, it's always gonna come out to that number because when you're doing half-life, these concentrations are always going to be 0.5 over 1. It's always gonna be the half of the original amount. So it's, this whole thing translates to T1 half is equal to 0.693 over K. Because of that natural log of 0.5 is always 0.693. So we can always just find the half-life, even though we could plug it in using the data, it's always gonna come out to this because the natural log of 0.5 minus the natural log of 1 is gonna equal 0.693. It's actually gonna equal negative 0.693, then we're gonna divide by negative k. So the negatives are gonna cancel out. And we're gonna get 0.693 divided by k every time. And now this equation is on your answer sheet. So it's half-life. Now, normally we associate half-life with radioactivity, but in this case, they do ask you for the half-life for, and here's the thing, a couple of things about half-life. Number one, this equation, this is the only one you're ever gonna have to use. They never have to do half-life for the second order or zero order. Zero order is just, it's gonna be linear, it's gonna be just whatever that slope is. But the first order is the only one where the half-life is consistent. So if the concentration is changing halves by an equal amount of time every time, then we know that it's a first order reaction. So you gotta write that down somewhere, okay? That's a really important statement because I'm gonna show you a practice problem here. I gotta try and remember the year it was in. It was just one of the more recent years. You have to determine the order of the reaction, and they didn't really give you any way to determine it. The only way to determine it was by knowing that the concentration halved in equal amounts of time. So as a result, that means it had to be first order. That's the only time that half-life is constant, is for first order reaction. All right.
You know. Half-life is constant every time. If in a half-life is constant every time. I'm just watching the video.
Oh no.
Limit of first order.
What did I say? A half-life is constant. Then
Not
It's a
17.
first order.
a half-life time is constant. It's the first word.
Yes. That's what I said. Something like that.
Okay, now, here's, I really thought that this is 2018. I thought this was a cheap question because they said radioactivity is not going to be included on the AP exam. But in 2018, they asked this question right here. Now, they give you a PES, okay? So this part's okay. Identify the element. Well, 1s2, 2s2, 2p3. These aren't written in there. Whoever did this test wrote those in there. So, but 2p3 is going to be which element? 2p3.
Nitrogen.
Nitrogen. Okay, so all you had to do is write nitrogen. This was one of the years I graded, and everybody the people that got to grade this question were finished so fast because you just had to write nitrogen. Is it nitrogen? It's either right or wrong. Nitrogen. No reading, no guessing, no nothing. Okay? And then calculate the value of the rate constant K for the radioactive decay. Radioactive decay, we didn't have to do radioactivity. But half-life, T1 half, 0.693 over K. Calculate the rate K, okay? Rate constant for the radioactive decay of this element, include units, okay? I'm trying to think of you just had to plug it into that value, but, this is what I'm missing out. It tells me the half-life. So K is gonna equal 0.693 divided by 10, 0.0693. I just didn't read the top part of that. I was saying I'm missing something. But they give you the half-life right here. So it's the exact same, whether it's radioactivity, anything that's half-life, we're gonna go to this equation right here. And that's given to you on the equation sheet. So it's just gonna be K is equal to 0.693 over T1 half. So 0.693 divided by 10 minutes, and we have to include units. This top number doesn't have a unit, so it's just per minute because it's first order. So it's equal to 0.0693 per minute. So this is 1 point. I think this was 2 points as far as because you had to have the unit. 1 point for the number, 1 point for the unit. And then this one, if 64 atoms of the radioactive isotope were originally present, what is the expected time that will pass until only 1 atom is present? How do we do that? 32,
68,
4, 2, 1, 6 half-lives.
6 times 10 is
6 times 10 is
now.
60 minutes. Okay? Now, if you don't know anything, you know, and again, radioactivity, I don't know, we didn't study radioactivity, but it's still just the exact same concept of half-life. Okay? Let me see. There's one more that I'm thinking about. I don't know. Question I lost. Okay, here's 2017.
No.
2017. Okay, I'm gonna make it small and I'll read it to you, but we have to be able to see all the graphs. Okay, you don't have this in your packet. You don't have this, I'm just going through the books. At high temperatures, the compound C, whatever it is, C4H6, I think it's C4H6. It's butadiene, so it's definitely 4 carbons because butane is 4. Doesn't matter. Reacts according to the equation above. The rate of the reaction was studied at that temperature in a rigid vessel. 2 different trials with each starting concentrations were carried on. The data were plotted in 3 different ways as shown below. Okay? So if I'm looking at this, what's the order of my reaction? Given these 3, and I'll try to make a little tad.
Second order.
Which one tells me the order of the reaction? Okay, why the third one? Because it's linear. So what's the y-axis?
1 over the concentration.
1 over concentration, which means it's what order? Second order. Okay, so the order of this reaction is second order with respect to the butadiene, the 1,3-butadiene. Okay, so the question is A. Okay, for trial 1, the initial pressure in atmospheres in the vessel at 625. Calculate the initial pressure. Assume that initially all the gas present in the vessel is C4H6. So we have the temperature, and then we're given the pressure. What's the initial concentration? This is gas. It's an all gas reaction. So how can I get the pressure from this? I'm going to give you a hint. It's an all-gas reaction. PV equals nRT. That shows up everywhere. If it gives you a gas and it's asking about a pressure, PV equals nRT. But watch. PV equals nRT. I'm looking for pressure. So pressure is going to equal nRT over V. Obviously, I know R.
0.0821.
I know temperature, 625 K, but I don't know N or V, or do I? Say what? N is moles, V is liters, so the molarity is your N over V. How do I know the molarity to start with before anything reacts?
Should say.
The initial molarity is right here, 0.02, right? So it's going to equal 0.02 moles per liter times 0.0821 liter atmosphere, so you do not have to put the units, Kelvin moles, times 625 K,
Plus 273.
okay? So liters cancel, moles cancel, kelvins cancel, leaving me with atmospheres, which is what I want. So we get 0.02 times 0.0821 times 625. The pressure is equal to 1.03 ATMs. So I'm looking at this graph, I'm thinking, oh, it's kinetics. I see my three graphs, it's the kinetics. It's going to be second order because that's linear. But they throw in gas laws to show up everywhere. You have a gas, they're asking for pressure, PV equals nRT. Just know that molarity, when it's a gas, N over V, in PV equals nRT, N over V is molarity. Little trick. Tricks of the trade.
So why is it like a gas?
Because it says gas right here.
I know, but like, why does that automatically make it PV reaction?
Because that's the only way you're gonna get pressure. If they give you the other stuff, the only way to get pressure of a gas is PV equals nRT. Pretty much. Okay, so there's my gas law question. Did this person get that right? 1.03 atmospheres. Woohoo! Okay. Now, use the data plotted in the graph. Use the data plotted in the graph to determine the order of the reaction. What's the order gonna, what did we determine it to be?
Second order.
Second order, that's all you gotta write. Okay? And then the initial rate of the reaction in trial 1 is given as 0.0010. Calculate the rate constant. Well, we determined it's second order, right? Okay? So C, what's my rate law gonna look like?
It's on the sheet.
No, but what's the rate law gonna set be? Oh,
One
if it's second order,
over natural.
Whatever constant.
no, again, I'm just, what's the rate law? It's the differential rate law.
Yeah.
Rate's gonna equal what? K times,
T.
no, differential, it's just C4H6 to what power? Second power, to the second order. That's our rate law. When it wants the rate law, you just, okay, we don't have anything with time really going on here. They give you the molarity. It's just the normal differential rate law. So how do I go about calculating K? Okay, the initial rate of the reaction in trial 1 is what? No? 0.0010. Okay, and that's molarity per second. Is equal to K times the initial concentration squared. Because in trial, we go back and look, make sure in trial 1, well, they just say the 2 trials. Trial 1 is this one right here, so it's the 0.02. Make sure, if it said trial 2, we'd have to use the 0.1. But it's trial 2, so it's 0.02. Now that's simple math. So K is gonna equal
0.001 divided by point
It's 2.5.
0.000.
So what does it come out to?
2.5.
2.5?
Yes.
And what are the units gonna be? This is gonna be what unit's gonna be over here?
All square, or
Molarity squared, but one of them's gonna cancel.
So, 1/7 times molarity.
Molarity times seconds, or seconds times molarity, doesn't matter, multiplication is commutative. Okay, very doable problems. Very, very doable. Let's see how this person did.
Did they get it?
God,
Well, there's one technical error.
It's a negative one.
They were redundant, weren't they?
Yeah. Oh. But they're not nice, so they won't give them the point.
Now you probably don't get the point for the unit.
So mean.
Okay? Have everything right. Molarity squared, molarity.
What if they meant to do 2.5 over seconds all times?
Yeah, times. Oh yeah.
Parenthesis.
Yeah, that he is right.
Okay, but as written, I don't think I would give credit for that. Because the order of operations, you're gonna multiply, well, actually, order of operations don't matter though. It's definitely in the denominator. They have molarity to the -1. It just needs to be over seconds times molarity, or molarity to the -1 has to be on the top, because the -1 means 1 over.
Say the answer came out to 2.5 molarity over seconds, and I wrote that. Would that be correct?
Yes.
You just said it. Thanks for that.
And I'd probably snicker as I graded it. Say, well, I guess this is right.
They write that nonsense in the questions all the time. This is our way to fight back.
Yeah. Alright, show the man. Then the bell ring quarter show.
Yes.
Yeah, it rings at 10 till.
Ah.
Okay, let me see if I can find one more. What year is this? I think this is 16.
It's a nice phone.
You guys have seen almost all these problems already.
Any chance they'll ever show up? No.
This is exact ones. This is exact
They
ones.
just get lazy on the exam, they just go back on.
And then just copy and paste.
Yeah, CTRL, C, CTRL.
Let's go back to 2009. Let's see what 2009 has.
That was a
to say.
great year.
I think I looked at this
Recession.
one. This was a different format in 2009.
Bro, that's smart. He exit.
First year.
No, that was the year I got mad. Try 2014.
That was a pretty good year.
What happened? I don't even remember 2014.
That one was great. Well,
You were in 5th grade.
This is the one I was thinking about. This is a good one.
You were trying to find it.
Okay, I can't remember. Did we talk about saturated fats, trans and cis or anything in here? Did I never talk about what a trans fat was? Okay, hey, listen. Okay, this is cis and trans. And you don't need to know what this is in order to be able to do the problem. That's really organic chemistry. But we hear the term trans fats all the time. And I wanted just to kind of explain. A fat is a long hydrocarbon chain. And if it's if it's unsaturated, that means it's unsaturated in terms of carbons. In essence, it's got double and triple bonds in it. So if I was to, do carbon, carbon, double bond, carbon, carbon, double bond, carbon, 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 and then a triple bond, well, not a triple bond, let's keep double bond, carbon. It would look something like this.
Did I miss something?
But if I built it, around the double bond is going to be, you can't bend around the double bond. So when the carbon chain continues on the same side of the double bond, it's called cis, and that's kind of Latin for same. Versus going across the double bond is going to be called trans, like the Transcontinental Railroad went across the continent. Okay? So it's the two different formats. When it's a cis format, it tends to be real bent, kinky. There's different kinks in the chain, okay? Whereas trans tends to be much more linear. If we do a saturated fat, if it's all single bonds, it also ends up being very linear, which is why they're bad for you, because they stack on top of one another and collect in your arteries and cause you to have a heart attack. Okay? So, saturated fats are way linear. So, they were known in the 50s and 60s, they were known to be realizing they were causing heart attacks and high cholesterol and all those problems. So they said, okay, well, we need to make more unsaturated fats, polyunsaturated, meaning many double bonds. So they came up with margarine. Margarine has a whole bunch of double bonds in it. However, they found that there's two different ways they can make the double bonds with the cis and the trans, this being bent, but this being linear. So it turns out that the trans fats, they are unsaturated, they have double bonds, but they're linear. They have the same negative effect of building up in your arteries as a saturated fat. So saturated fats taste better, they have a higher cooking temperature, they have a longer shelf life, so there's no need to have a trans fat. You don't want to have those. So if you're eating a bag of potato chips and it's talking about the amount of unsaturated fat, it's all going to be, if they don't say anything, it's the cis version. The trans fat are the ones that they're having to identify now. It's just the difference of whether or not the carbon chain goes on the same side of the carbons or on the opposite sides. Okay. We'll come back for part 2 in just a moment.